quantum spin. I've been looking over these sources, and I have to say, the deeper I go, the more I realize just how crucial spin is.
Absolutely.
It's everywhere.
Yeah.
From the structure of atoms to the cutting edge of quantum computers.
Yeah, it really is remarkable how such a seemingly simple concept can have such profound implications for our understanding of the universe.
But, even though we call it spin,
Right.
it's not like anything spinning in our everyday world.
Right. It's more like an intrinsic property of particles, like an inherent angular momentum that doesn't involve any actual physical rotation.
Okay, that's where I start to get tripped up.
Yeah.
If it's not spinning, what does it even mean to say it has angular momentum?
Well, the way we describe this intrinsic angular momentum mathematically is through quantum numbers and operators.
Okay.
It's a bit abstract.
Yeah.
But essentially, these operators act on something called spinors, which are the mathematical representations of the spin states.
So we have these spinors that describe the state of a particle's spin.
Yes.
But what are the possible states? Is it like a spectrum? Or are there specific discrete values?
That's a great question.
Okay.
And it gets to the heart of what makes quantum spin so unique.
Okay.
Unlike a spinning basketball
Yeah.
that can spin at any speed, an electron's spin is quantized. It can only be in specific discrete states,
Right.
much like a light switch
Right.
that can be either on or off.
So for an electron, we're talking about just two possible spin states.
Yes.
Up or down, right?
Exactly.
Oh,
Exactly. And those spinors I mentioned,
Right.
they're how we represent these up and down states mathematically. They're a completely different way of thinking about spin compared to classical spinning objects.
When I first encountered Pauli matrices, I was pretty intimidated.
Yeah.
But I'm starting to see how they fit into all of this.
They're definitely a powerful tool.
Yeah.
What puzzled me the most when I first learned about them was that each matrix actually corresponds to a specific direction in space, X, Y, or Z.
Wait, so you're saying that the way we describe spin mathematically is tied to spatial directions?
Exactly.
Wow.
And that connection between spin and direction is what leads to one of the most mind-blowing consequences of quantum spin.
Okay.
It's linked to magnetism.
Oh, right. The sources mention that electrons, because they have spin, act like tiny magnets. How does that even work?
Well, anytime you have a moving charge,
Okay.
it creates a magnetic field.
Okay.
And since an electron with spin has this intrinsic angular momentum, you can think of it like a charge constantly moving in a loop, generating its own tiny magnetic field.
So you're telling me that because of spin, electrons act like tiny magnets?
Yeah.
And that's what allows us to see inside the human body with MRI?
That's right.
That just seems incredible to me.
It really is.
Yeah.
The MRI machine uses a powerful magnetic field to align the spins of atomic nuclei within your body. By manipulating these spins and detecting the signals they emit, we can create detailed images of your internal organs and tissues.
Wow, I never realized that the simple act of spinning could be so powerful.
Yeah.
So we've got these tiny magnets zipping around inside atoms.
Right.
I'm guessing that leads to some interesting interactions, right?
You're absolutely right.
Okay.
And that brings us to the fascinating phenomenon of spin-orbit coupling.
Okay. I have to admit, the name sounds a bit intimidating.
Sure.
What's actually happening here?
Think about it like planets orbiting a star.
Okay.
The planet's spin can affect its orbital path, and the star's gravity influences the planet's rotation.
Okay.
Similarly, in an atom, the electron's spin interacts with its orbital motion around the nucleus.
So it's not just spinning on its own axis, it's also affecting how it moves around the nucleus.
Precisely, and this interaction between the electron's spin and its orbital motion leads to something called energy level splitting, which affects the fine structure of atomic spectra. Essentially, it influences the colors of light emitted by atoms, giving us a deeper understanding of how they interact with light.
So we've talked about this intrinsic angular momentum.
Right.
The up and down states, how spin is represented mathematically by spinors and Pauli matrices.
Yep.
And now how this interaction between spin and orbital motion plays out within the atom. It feels like we're starting to see how all these pieces fit together.
We are. And speaking of how spin affects interactions, let's talk about a phenomenon where those interactions become truly mind-boggling.
Okay.
Quantum entanglement.
Oh, entanglement.
Yeah.
Now that's where things start to get really interesting.
It is.
It's like two particles become linked no matter how far apart they are.
Yeah.
And measuring the spin of one instantly affects the other.
It's one of the most counterintuitive and fascinating aspects of quantum mechanics.
What are the biggest challenges to our understanding of reality that entanglement presents?
Mhm.
I mean, how can something measured here instantly affect something light years away?
It really does challenge our classical intuitions about locality and causality.
Yeah.
It suggests a level of interconnectedness that we're only beginning to grasp.
So we've gone from understanding what quantum spin isn't a tiny sphere spinning around to exploring its quantized nature, its
Yeah.
link to magnetism, and how it plays a role in this bizarre world of entanglement.
Right.
It feels like we've only just scratched the surface.
We have, and in the next part of our deep dive, we'll explore how these seemingly abstract concepts are actually driving some of the most exciting technological advancements in human history.
Okay,
Yeah.
sounds good.
All right. Welcome back to our deep dive into quantum spin.
Last time we really dug into the fundamentals of what spin is and isn't, and it's already blown my mind a few times.
Yeah, we went from thinking about a spinning top to this idea of intrinsic angular momentum.
And then there are those mathematical representations of spin states, spinors, and Pauli matrices. I have to admit, I'm still wrapping my head around those.
They are pretty abstract, but they're essential for understanding how spin behaves in quantum systems.
But what I'm really curious about is how all this seemingly abstract stuff connects to the real world. The sources mentioned something called spintronics. Is that what you're referring to?
It is.
Oh.
Spintronics is an exciting field that seeks to exploit the spin of electrons, in addition to their charge, to create new types of electronics. It's like we've been using only half of the electron's potential all this time.
I've always wondered how they actually use spin to build quantum computers.
Sure.
Can you break that down for me?
Quantum computers rely on something called qubits,
Okay.
quantum bits of information. And it turns out that the up and down spin states of electrons are a perfect way to represent the zeros and ones of a qubit.
So instead of bits that are either on or off, we have qubits that can be in a superposition of states.
Exactly.
Of 0 and 1 at the same time. I remember reading about that.
Exactly. And it's this ability to be in multiple states simultaneously, combined with the phenomenon of entanglement, that gives quantum computers their incredible power. They can explore many possible solutions at the same time, making them ideal for tackling complex problems that would take classical computers billions of years to solve.
The sources mention things like drug discovery, material science, and breaking encryption algorithms.
Yeah.
Those all sound pretty important.
They are. Quantum computing has the potential to revolutionize countless industries, from medicine to finance to artificial intelligence.
We've talked about how spin is linked to magnetism.
Right.
What does that mean for spintronics?
One of the most exciting aspects of spintronics is the ability to control and manipulate spin using magnetic fields.
Okay.
This opens up possibilities for creating devices that are smaller and faster and more energy efficient than traditional electronics.
So instead of just using the flow of electrons to carry information, we can also use their spin.
Exactly.
What kind of devices are we talking about?
Well, imagine hard drives that store information based on electron spin, magnetic sensors with unprecedented sensitivity,
Yeah.
and even transistors that use spin to control the flow of current.
So wait, are you saying that we could have computers that process information using the spin of electrons instead of their charge?
It's definitely a possibility.
Wow.
Spintronics is still a relatively young field, but it holds immense potential.
Yeah.
It's like we're unlocking a hidden layer of functionality within electronics by harnessing the power of quantum spin.
We've covered so much ground already, from the basics of what spin is to its potential applications in quantum computing and spintronics.
Yeah.
But I feel like we're just scratching the surface of what spin can teach us.
You're right, and there's one more layer we need to explore.
Okay.
The philosophical implications of quantum spin.
Okay.
It really pushes us to question our fundamental understanding of reality.
Okay. This is where we go full meta, right?
Exactly. Quantum spin challenges our classical intuitions about reality in a profound way.
You know, throughout this deep dive, we've kept coming back to the idea that quantum spin isn't about physical rotation.
Right.
But if it's not rotation, what is it? What is this fundamental property that's so deeply ingrained in the fabric of the universe?
That's a question that has puzzled physicists and philosophers for decades.
Yeah.
Some argue that spin is just a mathematical construct, a convenient way to describe the behavior of particles.
But if it's just a mathematical tool, how can it have such profound physical effects?
Right.
We're talking of technologies that are based on this construct.
Precisely. Others propose that spin is a manifestation of some deeper underlying reality that we don't yet fully comprehend.
Okay.
something beyond our current understanding of space, time, and matter.
So are you saying that the way we describe spin with math might be pointing to a deeper level of reality we haven't even grasped yet?
It really is.
That's pretty profound.
Quantum spin, with its paradoxical nature and profound implications, forces us to confront the limitations of our classical intuitions and embrace a new way of understanding the universe.
It's like we need to rethink our assumptions about what's real and what's just a mathematical trick.
Exactly, and that's what makes quantum spin so fascinating.
Yeah.
It's not just about physics. It's about pushing the boundaries of human knowledge and understanding.
All right, I'm ready to dive into the mathematical representations of spin now.
Oh.
Bring on the Pauli matrices and Bell states. Okay, we're back for the final part of our deep dive into quantum spin, and I'm ready to tackle those mathematical representations we've been skirting around.
Excellent. I think once you see how these mathematical tools are used, it'll really deepen your appreciation for how we understand and work with spin.
Let's start with those Pauli matrices.
Okay.
They seemed a little intimidating at first glance, but I'm ready to face them head on.
They're not as scary as they look.
Oh.
Remember, each Pauli matrix represents how spin behaves along a particular spatial direction,
Right.
X, Y, or Z.
So if I'm understanding this correctly,
Yeah.
these matrices help us understand how spin interacts with things like magnetic fields that have a specific direction.
Exactly. They're operators that act on the spinors.
Okay.
Those mathematical representations of the up and down spin states.
Right, those spinors. Can we see what those actually look like?
Absolutely. Here, let me write them out.
Okay.
So for spin up, we have 1,
Yeah.
0,
Okay.
and for spin down, theta 1.
So they're basically vectors, right?
Yes.
But what makes them different from any other vector?
What's special about these spinors is that they live in a two-dimensional complex vector space. It's a bit abstract,
Yeah.
but essentially it means we need complex numbers to fully describe the state of a particle spin.
Okay, I'm starting to see how this is a very different way of thinking about things compared to our everyday world.
It is, but
Yes.
despite this abstract nature, the math allows us to make incredibly precise predictions about how spin behaves.
Speaking of predictions, the sources mention this equation for an electron's magnetic moment.
Uh-huh.
What's so special about this equation?
Yes. The magnetic moment is a measure of an object's tendency to align itself with a magnetic field. And for an electron, it's directly proportional to its spin.
You know, I think what's been most mind-blowing for me in this entire deep dive is the fact that this tiny property of electrons, this thing we call spin, is the reason MRI works.
It is amazing.
I mean, doctors can see inside the human body just by looking at how these spins align with magnetic fields.
It's amazing, isn't it? And it all boils down to the equation that connects an electron spin to its magnetic moment.
Okay.
Terst G E2 meter S, where G is a constant called the G factor. E is the electron's charge. M is its mass. And S represents the spin vector.
Okay, there's a lot packed into that equation, but I'm starting to see how it connects the dots between spin magnetism and even medical imaging.
And then, of course, we have the Bell states.
Right.
They describe the entangled states of two particles,
Okay.
like two electrons that have their spins linked together in a very specific way.
Right. I remember you mentioned that these Bell states really capture the essence of entanglement.
Yes.
This idea that two particles can be connected no matter how far apart they are.
Here's what they look like.
Okay.
Plus a D plus AEO plus AOO plus AO. AUO plus AAO. AOO. AOO. I'm still working on deciphering all the symbols, but what I find fascinating is that these states represent something that seemingly defies our classical understanding of the world.
Absolutely. It's in these entangled states that the true weirdness and power of quantum mechanics really shines through.
So we've gone from understanding what quantum spin is to exploring its quantized nature and its link to magnetism, all the way to the mind-boggling implications of entanglement and its mathematical representation through Bell states.
And we've seen how these mathematical tools, as abstract as they might seem, are the key to unlocking the secrets of spin and harnessing its potential for groundbreaking technologies like quantum computing and spintronics.
This deep dive has been an incredible journey from the basics to the truly mind-bending. It feels like we've explored a whole new dimension of reality.
And yet this is just the beginning.
Yeah.
There's so much more to discover about quantum spin and its role in the universe. Well, on that note, I want to thank you for being such an incredible guide through this complex and fascinating world.
It's been my pleasure.
And to all of you listening, we hope this deep dive has sparked your curiosity and inspired you to continue exploring the wonders of quantum mechanics.
Until next time, keep questioning, keep exploring, and keep diving deep.